So we're looking at quadratic inequalities in two variables today. Whatever we did yesterday for linear inequalities, we are doing today for quadratic. That's basically it, okay? Consider the quadratic inequality y is less than x squared minus 2x minus 3. Circle the ordered pairs that satisfy the inequality. So we'll just take a minute and do that. I'm going to be doing it and speaking aloud as I do that, and you can do the same thing. Okay. I think you know where this is going. How many different ordered pairs exist that make the inequality true? Well, there will still be an infinite number. And I can demonstrate that to you by picking on one of these points. Let's go with 4, 1. When we put 4 in for x, we get a number that 1 is less than. That means this would be a solution. Because the number that we get when we put 4 in is still going to be a number that y will be less than, because now y is an even smaller number. And if I can demonstrate to you that there's at least one more point with the same x coordinate and a different y coordinate, then even just looking at that, you should understand there's an infinite number of y coordinates between 0 and 1 that would go with that x coordinate of 4 to make that equation or inequality true. So there's an infinite number. Plot the graph using a dashed line. Why are we plotting it using a dashed line? Because there's no equals to there. Okay. So how are we going to do that? It's y is equal to x squared minus 2x minus 3. Now is a pretty good time to review how to graph quadratic functions. I'm not saying we're going to pick up a graphing calculator and look at it. You should know how to graph this. One of the tools we have at our disposal is we can find the x-intercepts algebraically. And x-intercepts are found by letting y equal 0, but let's face it. X-intercepts of a quadratic function are the values of x that make the whole thing 0. So you look at the factors. This is an important idea for Math 30-1. You don't necessarily have to write equals 0. You look at this and you go, well, when will this be 0? When x minus 3 is 0 and when x plus 1 is 0. For goodness sake, I hope I factored that correctly. Pretty sure I did. So that means that we have x-intercepts of 3 and of -1. This is not an ordered pair, right? These are two numbers. So -1 and +3. We also know the y-intercept is -3. Why do I know the y-intercept is -3? Because that's the constant term of the function. I hope nobody would do this, and certainly don't draw what I'm about to draw. But I see people plot these 3 points and then they do this. Right? You know a parabola is symmetric, horizontally symmetric. And what that means, and I'm taking the opportunity to review a lot here today, is that if these are the two x-intercepts, then this is the axis of symmetry. It's halfway between the two x-intercepts. And what that means is that the vertex will be on that line. And if the vertex is on that line, and there's already a y-intercept to the left of the line at -3, then the vertex is going to be even lower. Okay. By the way, this is an interesting idea. If I said to you, find the y-coordinate of the vertex, I think most of you would go back to the function and complete the square, wouldn't you? Or maybe not. Maybe you've forgotten how to complete the square. Maybe you've blocked that out of your memory. But you don't have to complete the square because you know the x-coordinate of the vertex is 1. Just put 1 up in here for x. and you're going to get negative 4. So the vertex happens to be here. And since it's symmetrical, there's going to be a point there. This allows us to draw a fairly decent picture of the graph. And I'm looking out at a couple of yours, and you guys are amazing how well you can draw these. I'm no good here. I just, all I want to be able to do is just this part. And if I can get that far, I'm happy. Okay? If you can extend that up and still get that nice smooth curve on both sides, I applaud you, and I'm not being sarcastic. I just don't have that kind of ability built into my brain. And you can even see that what I drew there, it doesn't quite reach the vertex, so I'm going to cheat a little bit and just do that. So, what have I done wrong? It's not wrong. I'm going to change it. Right, it is going to be a dotted line, or dotted curve, I guess I should say. If you take a look at 4, 1, that very first point, was 4, 1 a point that was a solution to this inequality? It was. We circled it. And that means that when we plot 4, 1, we make it a solid point because that means it's there. When you look at 2, 2, 2, 2 was not a solution. So if you want to plot 2, 2, you can plot it, but it's not part of the solution. And let's be clear, when I ask you to sketch the solution, you're not going to put empty dots everywhere the solution doesn't exist. You're simply going to put solid dots everywhere the solution does. 1, negative 4. It turns out that 1, negative 4, I'm just going to choose a different color because this is kind of small. I believe 1, negative 4, it's not a solution. When we look at 0, 2, 0, 2 was not a solution. I'm not memorizing this, I'm just seeing where they go. When you look at negative 2, 3, I can't tell. Was negative 2, 3 a solution? It was. So when I go up here to 3, this will be a point, which tells me, everybody, that if I were to extend this dotted curve, continuing upwards on the left, it would miss that point. 3, 2 was not a solution, I don't think. There were a lot of 2's. 3, 2 was not a solution. Negative 1, negative 4 was a solution. And 0, negative 3 was not a solution. I mean, I think you get my drift here, that those 3 points that are solutions are below the parabola, and every point below the parabola will be a solution. Every point above the parabola will not be a solution, and every point on the parabola will not be a solution. On is equal to, above is greater than, below is less than for y. And this equation of the inequality was y is less than the quadratic function. So just to play the game here, what do you notice about the ordered pairs which are part of the solution? They are all below the quadratic expression. Not below or on. If it's below or on, then it's less than or equal. How can all of the solutions be shown on the graph? Shade. So here is where, if you draw the parabola that I have drawn, I think it's sufficient. I think it's sufficient to do this. I think I get the drift. I'm just hesitant in drawing more lines up here, and I think you can see why, because I haven't drawn the parabola up there. If I want to extend this, and right away I've kind of lost the shape of it, particularly on the left, then I can certainly shade more. I think this example is more about reviewing quadratic functions than anything else. By the way, below, because the inequality says y is less than. So you didn't need to use a test point. You certainly could have used a test point. Why were we instructed to graph the line using a dashed line? Well, because it was y is less than the function. And the line itself as a solid line is y is equal to the function. How would the inequality have been different if we did include a solid line? Well, then it would be less than or equal to. But this is just a carryover from yesterday, right? Okay. In fact, in my review of this lesson, everything I'm putting here, we had yesterday, it just said the solution to a linear inequality. So the solution to a quadratic inequality in two variables is represented by a shaded region either above or below the graph. If there's an or equal to as part of the inequality, then you need to include a solid curve, because then every point on that curve is part of the solution. If there is no or equal to, the line itself, the curve itself, is not the solution. It's kind of the boundary where you can creep up as close as you want to that line and still be a solution, but you can't touch the line. And that's why it's dashed. And you can use a test point. So let's take a look at this one. This one is a little bit easier to sketch. Well, maybe, maybe not. But again, I've designed this lesson to allow us to review some things that you need to know for the final exam. You should know that this is a vertex form of a quadratic expression where a is -2, p is 3, and q is 1. So the vertex is at 3, 1. Am I going to be drawing this thing with a dotted or a dashed line? Dashed, right? So even, see where I put that point? I mean, you need to understand that that point is not going to be part of the real graph, right? So if anything, if you like, in preparing, this is not going to be part of the curve. I just don't want to draw a solid dot there and have you think that's part of the solution. It opens down. I don't think we should just do this. Good enough. We don't know what it looks like. We can kind of figure it out by looking at that -2, but we don't know. So I think what we should do, is find the x-intercepts. And in order to do that, we have gone away from this inequality to this, right? We're analyzing a function here. What you could do, everybody, is expand this all out to get it into ax squared plus bx plus c and use the quadratic formula. I would prefer to do this. Well, I better be careful. 0 equals -2x minus 3 quantity squared plus 1. And rearrange it. There's only one x in there. We can peel off every other number until we're left with x. I can subtract 1 from both sides. I can divide both sides by 2. Take the square root and then add 3. Of course, when I take the square root, I have to go plus or minus, and I wrote plus or minus 1 over root 2 because the square root of 1/2 means the square root of 1 over the square root of 2. And the square root of 1 is 1. So my x-intercepts, and you'll have to decide where you're writing all of this, are 3 plus or minus 1 over root 2. But that root 2 is only under the 1, not under the 3. Well, let's find out what that is in decimal form, approximately. It's about 2.3 and 3.7, I believe. We're okay with that? Okay. So that just, it turns out what I drew initially is pretty close to what it should be. 2.3, it's a pretty narrow parabola. 2.3 is about here. 3.7 is about here. This is what the parabola looks like. If you wanted to determine the y-intercept, why would you want to do that? I don't know, because you want to. Maybe you want, every time I try to clean this up, it just gets a little bit worse. Maybe you just want to see more of the function. Then you would put 0 in for x to find the y-intercept, and I believe you're going to end up with negative 17 for a y-intercept. It's way down there. Let's try this one with a test point. Let's take this test point. So you're putting 0 in for x and 0 in for y. And I get 0 is less than, help me out here. It is negative 17, isn't it? I don't know. It is, okay. So is 0 less than negative 17 a true statement? No, it's not, which means that test point is not a solution, and that means that the solution to this equation is found by shading below. And again, I'm hesitant to shade further below unless I'm willing to graph the parabola going further below. I can certainly do that. It's just that, like I said before, I'm parabolically challenged when it comes to drawing these things. I just don't do a good job. And that's fine. I'm happy with my life in every other respect. Are we okay with that? I feel as though I don't think we need to do all of these examples. Let me do this very roughly. In fact, let's do this one together just as a rough sketch. In other words, we're not worried about exactly the right shape or points. I hope you understand that the vertex of this parabola is at 4, negative 2, and that it opens up, and that since a is 1, it has the same basic shape as y equals x squared. It's not really narrow, it's not really wide. So when I go to 4, negative 2, it is about here. And this is a parabola that opens up. Are we going to, I can't believe this is greater than, are we going to use dotted line, a dotted curve, or solid? Dotted. Is the next one at least got an equals? Okay, good. So what this would look like if we were to sketch this graph is it would look like this. Roughly. Where are we going to shade, above or below? How many of you see it's above because it says y is greater than? If you do, that's really good. I want to get rid of this. If you do, that's really good. If you don't, that's okay. Choose 0, 0 as a test point. Put 0 in for x, 0 in for y. You will discover that you will get 0 is greater than 14. And 0 is not greater than 14, so it's not a surviving point. So this is the sketch. Is 2 comma 1 a solution? Well, if we would have done it on this grid with numbers, we might be able to look and answer that question, but we can't because we didn't. So you put in 2 for x. 2 minus 4 is negative 2. Quantity squared is 4. 4 minus 2 is 2. When I put 2 in for x, I get 2. And that means I'm going to be left with this brilliant statement, and that's not true. 1 is not greater than 2. So when I put 1 as y and 2 for x into that inequality, I'm left with a false statement. So the answer is no. It is not a solution. I think you're catching my drift, even though the next example is the one that actually has the equals to. You understand this will be a parabola that opens up. It will be a solid line, and you will shade above the parabola. This is one you could factor and find the x-intercepts and find the vertex like we did with our previous example. But let's skip past it. I have one more example I want to do with you. There's a relation here, it's an inequality, showing the connection between the mass measured in pounds. This is a math class. We don't need to worry about mass is actually measured in kilograms and pounds is a force and stuff like that. The mass in pounds must be less than or equal to 1,450 times the diameter of the rope squared. Okay. So if the mass is not less than that number, the rope will break and you will fall when you're climbing the mountain. Okay. Graph the inequality on a graphing calculator and explain what it means. So we're going to start off by putting in y is less than or equal to 1450 x squared. And I know I can't put less than or equal to, but we can shade less than by choosing that option that we talked about yesterday. And now we want to set up our axes. D is x. I don't care whether you've ever been climbing mountains or rock climbing or do any of that stuff before. You understand that rope can be quite heavy. I don't think you want rope that has that diameter. We run into a problem there, by the way, because then not only does the rope have to support you, it has to support all the other rope. It's complicated. So D is the diameter in inches. Let's go up to an inch. Let's just see what happens up to 1 inch in diameter. So we are going to manually set up our window settings to go from 0 to 1, maybe up by 0.25. Now, what are we going to do for our vertical? We're going to do the same thing I've tried to teach you all semester. And we're running out of time here. We've got like a week left of classes, basically. And that's to go to the table setup. I'm going to start at 0 and go up by 0.1. I'm going up to an inch. So I'm exploring a table where x is 0.1 of an inch, 0.2 of an inch, 0.3 of an inch, all the way up. And now I can go to my table and see that m in this relation goes up to 1,450 pounds, which shouldn't be a big surprise. So now I'm going to back off. Because I think if your weight is 1,450 pounds, you probably shouldn't be trying to get on a mountain. Okay? You need serious medical intervention. Okay? Let's go up to maybe 200 pounds. There's many people that are very fit and active and do mountain climbing and rock climbing that are 250 pounds. But that means I'm only going to go up to about 0.4 inches for a diameter. So now I'm changing my mind here. Instead of going up to an inch, let's go up to 0.4 of an inch. About 3/8 of an inch, a little bit more. So I'm going to go over here and I'm going to go up to 0.4. We can go up by 0.05 or whatever you want. I don't care. And for M, we're going to go up to, I think I saw about 232 pounds with that. So let's go up to 240 pounds, up in increments of maybe 50. And now when I graph, I get this. It's a pretty nice representation of what's going on. And now we want to explain the meaning of this. And I don't know what you want to write. I don't care if you write anything. This is what the graph looks like. You can take a moment and do a little sketch of it. I'm going to find a particular point on this graph so we can talk about numbers. I'm going to go trace 0.25, quarter-inch rope, 90.6 pounds. There's a point here, point P I'll call it, which is 0.25 inches, comma, 96 pounds, roughly. Pardon me, 91 pounds, roughly. What that means is that since that point is a point on the inequality, a 91-pound person, they're over here, this is 91 pounds, can use that diameter of rope. Can the 91-pound person use this diameter? Well, if I were to go 0.18, that point is here, isn't it? 91 pounds and 0.18. That is no longer in the solution region. So that means if you use 0.18-inch diameter rope, the rope is likely to break. Don't get me wrong here. According to the mathematics of this rope will not break, right? Does that mean you want to go with a 0.25-inch diameter rope? No, you probably want to do this, right? You probably want a bigger diameter rope. But you don't want to use this diameter rope if you don't need to, because it adds weight. So what it means is that every point under here, if you read this, this would be an acceptable solution. If that was 0.35 inches and this happened to be 80 pounds, then that would be good. But an 80-pound person could also use this diameter rope. I don't think it's the best thing to be using to learn about, because you understand you'd probably want to, no, it's okay. You'd probably not want to be right along the curve, right? But let's imagine that somebody has already taken that into account and they've built a whole bunch of cushion room into that inequality, okay? It's like in Physics 30 when we talk about the maximum speed you can have going around the track, and we get 25.2 meters per second. That doesn't mean you should travel at 25.2. It means you probably want to travel only at 20, but they build that into the speed limit signs. When you see that slow down to 75, that's not the tipping point, okay? The tipping point is probably 55 or 60. So I hope that reviews a bit of graphing quadratic expressions and gives you a good idea of what we're talking about with inequalities here. There's a number of questions to work on here. We're getting very near the end of this unit, so work on some of these. I still encourage you to go back to 2 lessons ago and practice more and more of the solving, algebraically solving systems of equations. I think that's really important to develop those skills. So get started on that. You've got a fair amount of time today. Did anybody have any questions about that final example?